Welcome to Precalculus, boys and girls. We're starting with our first chapter in our first section. This is 1.1, Real Numbers, Relations, and Functions. You're going to notice that I go pretty fast through this. One of the reasons is because you are able to pause the video. In class, I would go much slower, but since you can pause the video, you can take as much time as you need to write stuff down. Our first chapter here is 1.1, Real Numbers, Relations, and Functions. So real numbers, you've been using them for your whole life. They include the natural numbers, which are referred to as counting numbers. Counting numbers is the first numbers you learned. You started to count with 1, 2, 3, 4, and so on. When you were a child learning to count, you didn't start with 1.1. You didn't learn 0 when you first learned to count. You first started with 1. Because 1 was something. It meant you had something. So our natural numbers are the numbers that naturally come to us as we learn, as we're growing. We have 1 Cheerio. We have 2 Cheerios. We have 1 toy. We never think as a baby, I have 0 toys. That's why those aren't the natural numbers. But soon after we learn 0, which started the whole numbers. The whole numbers are 0 combined with our set of natural numbers. So our whole numbers start at 0 and go on forever. Integers are the whole numbers and their opposites. So I'm taking my whole numbers, which was 0 going on forever, and now combining with their opposites or with the negative versions. So -1, -2, -3, -4, -5, going on forever this direction. So it's the whole numbers with adding on all the negatives that go with it. A real number becomes a rational number if it can be expressed as a ratio, r over s, where r and s are both integers. And the following would then be rational numbers. So 1/2 is a rational number because it's an integer 1 over the integer 2. -9.83 would be a real rational number because that is -938 over 1,000. 47 is a rational number, even though it's not something over something, because any whole number, or counting number even, is always over 1. Because 47 divided by 1 is just 47. Lastly, if I have a mixed number, like 8 and 3/5, that is also a rational number because I have the 3 over 5, but also because 5 times 8 gives me 40. Add the 3 on, that's 43. 8 and 3/5 is the same as 43 over 5. In fact, any decimal that ends is actually a rational number. So does that mean that every decimal that doesn't end is an irrational number? That's not exactly true. A real number that cannot be expressed as a ratio with an integer numerator and denominator is an irrational number. Now the example that I was talking about up here would be one that's like 0.33333 repeating, going on forever. Yes, that looks like it goes on forever, so it doesn't end. However, I can express that as 1/3. Irrational numbers are numbers that can't be converted from this decimal format to any type of fraction like this. Pi is an irrational number. Now most of us remember pi as 3.14, but it actually goes much further than that. This table gives pi to 1,000 decimal places. It goes on and on. There's actually a computer program that it's still trying to discover more digits of pi because it goes on forever. Going back to pi, you'll notice that the numbers never really repeat. We have 3, 3, but then it turns into an 8 after that. That's one of the reasons that it's not, or that it's not rational, and it creates this irrational number. So it'll be double digited or even triple digited, but when they find that next digit, it's not the same. The most that it's ever gone to is where they had 6 in a row. But then again, it flipped back to an 8. So that's what makes it irrational. Now, all these number sets are related to each other. All natural numbers are actually whole numbers. All whole numbers are integers because the natural numbers are the whole numbers, but not including 0. The whole numbers are the integers that don't include the negatives. The integers are all rational numbers. If I think about the integer set, that's -3, -2, -1, going on forever this direction, and then 0, 1, 2, 3, and going on forever this direction. Those can all be expressed as fractions, -3/1, -2/1, and so on. All rational numbers are real numbers. Real numbers include all of these different sets. They're all included in real numbers. And all irrational numbers are real numbers. And so if I look at the chart, natural numbers are included in the whole. So the whole includes all of this plus what's inside the natural numbers. The integers include all the numbers outside of the whole numbers, including the whole numbers. And the rational include everything inside of here. But on the other half, we have irrational numbers. A number can't be a natural number and irrational. It can't be a whole number and irrational. Irrationals are all by themselves over here. But even those are part of a bigger circle, which is all of the real numbers. The real number line. Each point on the real number line corresponds, or each number corresponds to exactly one point on the real number line. It creates one correspondence. So if I have 1.33 at this point, 1.33 cannot also be here. It has to be at one exact precise point on the real number line. Same thing with -9.5. It can only correspond to one spot. It can't be here and here. The coordinate plane. Now I realize that you've done most of this stuff before, but it's just good to review it in the beginning here. Just as real numbers correspond to a point on a number line, ordered pairs of real numbers correspond to points in a plane. Now you might not remember that terminology, ordered pairs, but ordered pairs are just an x and a y. Remember, this is your y-axis, this is your x-axis. We have 4 different quadrants in these. The first quadrant is here, and then you go counterclockwise. Second quadrant, third quadrant, fourth quadrant. This point where C is here and D is here forms the ordered pair CD. The number on the X is always going to come first. The number on the Y always comes second. Scatter plots. In many application problems, data is plotted as points on the coordinate plane. This type of representation of data is called a scatter plot. So here we have a table of data, 1998, 90, 92, 94, 96, and then we have different amounts for each. When we create a scatter plot, we're starting out and setting this as our X and this as our Y. If I look at my graph, there is no 1988 on there, but that's the first year, so that's 0. That's our starting point right here, which would make 1990 2, then 4, and 6, and 8. So year 0, or our starting point, it's 276. Now, a good way to remember year 0, think about your starting point. When you were born, were you 1 year old? Or 1 year old, I should say? No, you were 0. You were minutes out of the womb. So your starting point is at year 0. So at 0, we go up to 276, make a dot. At 2, you go up to 284, make a dot. Is there a huge difference between these two? No, because it's only a difference of 9, and we're going, if we look at our y-axis, it goes up by 100. Year 4 is 392. Year 6 is 418. And year 8 is 500. So that's a scatter plot. Each spot on here, each point that I drew, corresponds to one set of the data. A relation, its domain and range. So a relationship exists whenever one variable is related to a second variable. The first quantity, often called the x variable, is said to be related to the second quantity, often called the y variable. A relation's domain is all of the x values, and the range is all of the y values. So if I look at these numbers, my domain is going to be all of the x values. My range, so these are all the x values here. And if I look at the bottom table, you'll see height in inches is also there. So these continue as my x values. My range is all of the y values. So we have all those values in red is our domain, and all the values in blue is our range. Our ordered pairs is the relationship between the two. So 67 and 8.5. 67 would come first because that's the x. Then 7210, 6912, 7612, 6710, 7211, and so on and so forth. So these are all the relations that exist between the two numbers. Takes a little while to list them all out. Those are all of our ordered pairs. if I look at the domain, that is all of my X values. So you kind of do a squiggly bracket here to do a domain. It's all of the X values in our ordered pairs. 67, 72, 69, 76, 67. Now, you'll notice the 67 repeats, so I don't have to repeat it. 72, that repeats. 67 repeats again. 62.5, that's a new one. 64.5, that's a new one. 64, 62, and 62. That's my domain. My range is all of the Y values. So range would be 8.5, 10, 12. 12 repeats, so I don't have to write it again. 10 repeats, I don't have to write it again. 11, 7.5, 5.5, 8, 8.5 is repeating, so I don't have to write it again. 6.5 and 6. And that's my range. That 6.5 is pretty ugly. Okay, that seems like a good place to leave off. I'm going to give you a homework assignment. You're going to have to identify what types of numbers they are. So list out all the different types of numbers that they are, and give me some ordered pairs, domains, and ranges. If you have any questions, come to the Google Meet tomorrow.